Welcome back. Let's finish up stuff on categories. Quick passing comment. I had a few of the morphisms in the wrong order when we were doing compositions in the past. Those are corrected on the online notes. I mean, you always have access to the online notes. The websites are given. I pulled these directly off the internet. So the observations we made last time about some morphisms being listed in the wrong order, that's corrected, and I found 2 or 3 others places where I had them in the wrong order. The diagrams were fine, so you can tell the order from there, but those little boo-boos are corrected. I'm sure there's others out there. Let's pick up right where we left off. We had just defined product in a category, and we had made an observation that the product, though defined in terms of several collections of morphisms, there's a certain kind of independence in the choice of some of the morphisms in that definition, giving us that if I take a collection of objects from a category, I want to say the product is uniquely determined. It's determined up to equivalence. If we compute the product over this family of objects using different morphisms, pi sub i's or psi sub i's as given previously, we'll look back at that definition here shortly. Then we end up with a collection, or we end up with 2 products which are actually equivalent. Equivalent meaning something rather specific in terms of compositions of mappings that give identity morphisms, not to be confused with identity functions. But it's awfully suggestive in how they behave. So what we're going to do next is reverse all the directions of all the morphisms. If we do so in a category, which really corresponds to reversing all the arrows in the diagrams that we have. And remember, those diagrams were required to commute. That's how we got the composition claims that we made. But by reversing directions of morphisms, we create a dual statement about a category. The following is the dual definition of product. So like I said, let's slip back a page or so and look at the definition of product. So what we'll do is take this. We got mappings from P to A sub I. We'll change that into mappings from A sub I to P when we do coproducts. So we took a family of objects in category C. We took a family of morphisms, pi sub I, mapping the product to the A sub i's. This is the thing that we had the independence in that Theorem 7.3. It didn't depend in a sense on the pi sub i's. We got an equivalent product if we used a different collection of such morphisms. Anyhow, we've got these mappings from the product to the A sub i's. And we took any object B and any family of morphisms mapping B into the A sub i's, and there existed a unique morphism phi mapping B into P, and we had some composition condition down here. Okay, so we want to mimic this, but reverse the direction of the orderings of the morphisms in our definition of a coproduct. So let C be a category of objects, A sub I a family of objects in C, indexed by indexing set capital I again. A coproduct or sum, we'll use the term coproduct primarily. A coproduct of this family is an object S in C. So by definition, a coproduct is an object in the category, together with a family of morphisms, iota sub I mapping A sub I into S, such that for any object B and any family of morphisms, psi sub I mapping A sub I into B, there's a unique morphism psi mapping the coproduct into B, such that psi composed with iota sub I equals psi sub I for all values of the index, and we denote this thing as an upside down pi coproduct. So this is exactly what we had before, except we're denoting the coproduct with an S instead of a P, like as we did in product. And the collections of morphisms map not from the product to the A sub i's, but from the A sub i's to the product. And similarly down here on these morphisms associated with arbitrary object B. So if we'll line up this statement with the definition of product, what we've done is we've replaced in product the mappings from P to A sub I, the pi sub i's, with iota sub i's, mapping the A sub i's into the coproduct. The P has been replaced with an S, P for product, S for coproduct. So the mappings go in the opposite direction there. The phi sub i's that came with object B, that mapped B into A sub I, are here replaced with these psi sub i's that map in the other direction, maps the A sub i's into object B. The unique phi that composed in a certain way in the previous definition mapped B, object B, into the product. Here is replaced with a psi that maps the coproduct into object B. So all the mappings have been reversed. Theorem 1.7.3 for products. Actually, let's look at it again. Last thing we did in the previous video says if we compute these products two different ways, that is using different collections of morphisms, pi sub I or psi sub I, then we get equivalent products. So the dual statement should say something about different, should come here, different iota sub i's yielding equivalent coproducts. And what Theorem 1.7.5 says is C is a category of objects, A sub I is a family of objects indexed by capital I. If we compute a coproduct using the iota sub i's, or if we compute a coproduct using something different, say lambda sub i's, these coproducts are equivalent. This S coproduct or S prime coproduct, they are equivalent. So proof of this, reverse all the directions of the morphisms and follow through something quite similar to Theorem 1.7.3. So there's an independence in the definition of coproduct in the choice of some of those morphisms. Okay, shifting gears yet again to something a little bit different called a concrete category. I like sets, and a concrete category is pretty much a setting where we're dealing with sets. In many categories, the objects are sets or sets with an added structure. Of course, of interest to us is groups. A group is a set of elements. Well, there you go. Yeah, together with additional structure, they come with a binary operation that satisfies some conditions. But when this is the case, when the objects are sets or associated with sets, the morphisms can be considered as functions on those sets. This leads to the idea of a concrete category. So definition of a concrete category is, concrete category is a category calligraphy C together with a function sigma that assigns to each object A of C a set sigma of A called the underlying set of A such that the following conditions hold. Now we actually go through this stuff, in particular some of the proofs. We won't draw a distinction between object A and the underlying set sigma of A, provided we're in a concrete category. So the sigma notation is going to be short-lived in our conversations. Provided we're in a concrete category, there's no room for ambiguity there. Well, there's not much room for ambiguity, but we'll use the symbols A and sigma of A interchangeably after the definition, provided we're in a concrete category. So requirements are, every morphism mapping A to B of category C is a function on the underlying sets sigma of A being mapped to sigma of B. So the morphisms are functions. So something will touch more concrete to probably all of us. The identity morphism of each object A of C is the identity function. Okay, the identity morphism was defined in terms of some types of compositions. Identity function is very straightforward. I can very explicitly tell you what the identity function on a set is. It maps an element to itself. And a little surprisingly, maybe the identity morphism, that was not quite so tangible. And thirdly, the composition of morphisms in the category agrees with the compositions of the functions on the underlying sets. So morphism composition correlates with function composition. So that's what a concrete category is. It's kind of a suggestive word. It's much more concrete, more tangible than some of this more abstract stuff we were doing above. We've all got more experience with functions than we do with morphisms. An example, if we take the category of groups, the category of all groups that we had previously, if we'll define sigma of a group simply to be the set of elements of the group, I'm using a notation probably from Fraley here, where a group is given in these angled brackets as a set of elements along with a binary operation which satisfies certain conditions. So we take the group and simply associate the group with a set of elements of the group. Doing that gives us a concrete category. In that category, the mappings were homomorphisms, you'll recall. So that's mapping groups to other groups, mapping the set of elements of the groups to the set of elements of the other groups with some additional structure, preservation of the binary operation for homomorphisms. But anyhow, this does allow us to talk about the category of all groups as a concrete category. An example of a non-concrete category. Previously, example 1.7.a, we defined a category using a single group, G, say with binary operation asterisk, where we took as hom, G comma G, that it be the morphisms mapping G into itself, is the elements of G themselves. So a morphism is an element of the group. And then we compose those morphisms using the binary operation of the group. But that's not a concrete category. First part of a concrete category required the morphisms to be functions. Here, in this example, the morphisms aren't functions, they're actually elements of the group itself. So we don't have a concrete category in this particular example. So the morphisms are elements of the groups themselves, as it says down here, not functions on the elements of the group. So that gives an example of a category that's not a concrete category. Shifting gears again onto another topic. This last part of the section goes by a little bit more quickly. This we'll use in section 1.9. We'll define free groups in section 1.9. And here we're going to define what it means for an object in a category to be free on a given set. So fortunately, definition 1.7.7 deals with concrete categories. Excellent. Then that means everything in Cite's either a set or a function. The objects are sets, the morphisms are functions, so it's somewhat concrete here. And then we're going to take this concrete category and put an additional requirement on the interactions of objects in certain sets as follows. Of course, this is the punchline here in terms of this little diagram. Let F be an object in a concrete category C, X a non-empty set. So this just came out of nowhere. The set X doesn't say that X is itself in the category, just X is a non-empty set. And I map set X to object F. Define this as a set map. Okay, strictly speaking, we might want to think of that as sigma of F right? If I call it a set map, I mean, it maps a set to an object. Yeah, F, strictly speaking, F is not a set itself. It's an object, but sigma of F is a set, and then I becomes a function. So we're kind of maybe glossing over those details. Fine, fine. As long as we're in a concrete category, I don't have a problem with that. So the definition is, object F is free on the set X, provided that for any object A of C and any set map, mapping X to A, there exists a unique morphism of C, called F bar, mapping F into A, such that F bar composed with I equals F as a map from X to A. In other words, okay, so we started with object F, non-empty set X, and mapping I. So we started with this first line here. So we've got set X mapped into object F, if you will. Next came any object A. So next comes the bottom of this. We introduce object A, and along with it, set map F. So F mapping X into A. The requirement is there exists a unique morphism, F bar, is given here. So this is somewhat consistent with what we had in some of the product stuff and some of the previous stuff about this unique morphism stuff. And the requirement is mapping I followed by mapping F bar is the same as mapping F. Set map, okay, I could certainly interpret F and A as sets. They're objects in a concrete category, so we're good with that. I followed by F, yeah, that'd be F bar composed with I. Just make sure I got my orders correct on these, and we do. So there's the definition of a concrete category. An example and some motivation as to why you would want to look at, sorry, not concrete category, definition of an object being free on a set, excuse me, in the setting of concrete categories. Now, a situation where we're trying to motivate why you would want to look at objects free on sets. Let's go to maybe that category of all groups example that we've had in the past. Let A equal G be some group, and let lowercase g be an element of the group. Take F to be the group of integers. The integers is a group under addition. So what we have here is we're given F, we're given A. A could be anything. So here we've just chosen A to be in some group G. So the symbols are going to change to this group setting. We want to find F bar, a homomorphism from the integers to G, such a mapping. If F is free on X, then F bar is uniquely determined by a mapping I and this mapping F. So what we have is integers here, group down here, some group G, capital G down here, and we want to get this uniquely determined. If we have that F is a free group, if F is free on the set X, right, free groups will be the topic that we use this in. But if F is free on X, then given the I and the F, that uniquely determines this F bar. So we want to take advantage of that in this setting. If, for now, if object F is free on non-empty set X, then F bar is uniquely determined by I and F. That was the definition of free on set X. So we're going to choose X as a subset of the group of integers. Here we're just going to take X to be the integer 1. By the way, that generates the integers as an additive group. So Let I be the inclusion map. What that simply does is takes this set consisting of the integers and maps it into the integers as the set consisting only of one. Sorry, the set consisting of one, embeds it in the integers. That's kind of why they call it I think, embed. But we'll take the mapping I simply to embed that as an element of the integers. And then we need to define f of 1. Say we define f of 1 as g. Okay, so that gives us mapping I, simply embeds the element 1 into the integer z. Mapping f, it takes that 1 and associates it with g, an element of the group capital G down here. Like I said, the symbols have changed. That's correspondence between them. So that gives us mapping I, that gives us mapping f, rather arbitrarily. If f is free on x, then we get that this f bar is uniquely determined. But 1 generates the integers. Homomorphism f bar then is uniquely determined because you know what it does on a generator of the integers. So if I know what it does on the generator of the integers, I know what it does at all the integers. F of 2 would be g squared if we're using multiplicative notation in group G. 2g if we're using additive notation. So the f bar is uniquely determined, and hence f is free on x. We get that unique determination. So this object, f, is free on this set. Now, that shows that we didn't have to define too much stuff here. We only had to make sure we could define that mapping f on a single element. This example illustrates the value of having object f free on set x. To define a morphism on f, it suffices to define a morphism on what was ultimately a subset of f. Well, yeah, a cleverly chosen subset. In this group setting, we just chose a generator. So by having a generator of the integers, we could determine the behavior of mapping f bar simply by defining f to group G by letting f mapping this set to group G by letting this set consist of a generator of the integers. So not a surprising outcome, but something to illustrate what's going on in terms of these free objects. Suppose we're in a concrete category. F and F prime are objects of C such that F is free on the set X and F prime is free on the set X prime. Sets X and X prime have the same cardinality. Then F is equivalent to F prime. Okay. When we looked at the category of all sets, two sets were equivalent if they had the same cardinality. We define the morphisms in terms of bijections in that category. If I put it in that setting, then we're saying when the sets are equivalent, then the F and F primes are equivalent. So what we're requiring here is sets of the same cardinality. By the way, that gives us a bijection of those sets. And to show equivalence, tell you what, let's run back real quick and look at the definition of equivalence. I've mentioned it today verbally, several slides back. Definition of equivalent, many slides back, product. Example, here we are. Okay. To say two objects A and B are equivalent is to show the existence of a mapping G from one object to the other and a mapping F from the other object to the one, such that the composition G composed with F equals an identity and F composed with G equals an identity as appropriate, identity on A or B, object A or object B as needed. So we need to demonstrate something like that, and guess what? We're going to do it using the uniqueness stuff that we know when we're dealing with objects that are free on sets. It comes with a uniqueness claim. That uniqueness claim will also be satisfied by an identity function. That's how we'll get this equivalence established. Okay, back to Theorem 7, Theorem 8, 1.7.8. Okay, let's look at a proof. Good news is it's mostly diagrams and pasting diagrams together. Well, we've got sets X and X prime, and they're the same cardinality. So there's a bijection between them. Let's call that bijection F. Now, that's what it means for sets to be the same cardinality. Now, object F is free on set X, hypotheses. So there's a set map I from X to F. Since F prime is free on X prime, there's a set map J from X prime to F. Definition of free. Consider the composition of those two maps. Right? The X prime doesn't appear in this story, not yet, but we're going to consider the mapping J composed with F. What that does is F comes first, so this takes us from X to X prime, and then J, and then from X prime to F prime. So indeed, the composition J composed with F does map X through X prime to F prime. So ultimately we get a mapping from X to F prime. Okay, so we've got this mapping, we've got the set mapping here, and we know by a hypothesis of free, F is free on set X, that means this mapping here satisfying the fact that the diagram commutes is uniquely determined. So what we must get out is I followed by phi is the same as this function here. That is phi composed with I followed by phi is the same as the mapping J composed with F. First off, using the hypotheses of F is free on set X. Okay, next what we're going to do is, remember, F took us into X prime and then J took us over to F prime from there. Let's take this and break it. And instead of having this diagram with the three objects or sets or whatever, let's introduce X prime. So same thing we had before, but now we've explicitly written the X prime. F mapped X to X prime. It was a bijection that we had because their cardinalities were the same. J was mapping X prime into F. So we get this type of mapping here. This is the same information we had previously. And the phi is uniquely determined from this other information. That's the free part. For reasons to become apparent soon, let's rotate that 90 degrees counterclockwise. Put the phi on top, put the I on the left, and so forth. So let's rotate it around. Same information, same commuting diagrams. I'd read it maybe in this direction, up and over versus over and up, and say we get the equality of those resulting compositions. So we've got a diagram of this sort. The goal here, again, is showing F is equivalent to F prime. Okay, that means I need identities on F, a composition that gives identities on F, and a composition that gives identities on F prime. 1 sub F and 1 sub F prime was the notation that Hungerford likes. We've got this kind of mapping. I don't see anywhere inside a mapping of F to itself. But let's do what we just did, except now let's start with set X prime here. We know F mapping X to X prime is a bijection. It was the bijection that we knew existed based on the fact that those two sets are the same cardinality. So it's got an inverse, a legitimate inverse, not an inverse image stuff. Bijection has an inverse. And it maps x prime to x. A little typo there. Should have F inverse mapping x prime to x. So check the updates. I'll get that fixed in these supplemental notes. So F maps x prime to x. Then we'll compose it with I. Mapping I took x into F. It was at the top on the previous slide. So we'll go from x prime down to x and then over to F with mapping I. That is, I composed with F inverse maps x prime into F. Actually does it by going through x itself. So I've described it, but that's the mapping we get. Hey, object F prime is free on set x prime. Hypotheses, F prime is free on set x prime. So up here, we've got this part is given, as it were. Then there exists a psi, a unique psi down here, such that this diagram commutes. In other words, j followed by psi is the same as this function here. J followed by psi is the same as I compose with F inverse. I compose with F inverse. Okay, so stuff ain't that bad. What you gonna do next? We'll bust this up into a square like we did before. So let's introduce x down here in the lower left. Introduce the x. There's explicitly the mapping F inverse and the mapping I. How about we rotate it 90 degrees counterclockwise again? Yeah, same little rotation here. The psi comes up top, the j goes over to the left, and so forth. This is quite similar to what we had before, except this time we got the F prime on the left and the F on the right. Before it was the other way around. We had the F on the left and the F prime on the right. Remember, we're trying to establish equivalence. We want a mapping from F to itself and a mapping from F prime to itself. We got here, knowing that this psi is uniquely determined. The free hypotheses gave us that this psi is uniquely determined. So let's draw that picture along with the first picture that we had. Also, this phi is uniquely determined. So let's take these two diagrams and paste them together, as we've kind of done in the past. What that accomplishes is we'll have a mapping from F to itself. It'll be a mapping from F through F prime to F. It'll be first comes phi, second comes psi. Reverse the orders is written on the left there. But we'll get psi composed with phi, mapping F into F. And down below, we'll have F followed by F inverse. It's be F inverse composed with F. But wait, F was a bijection and F inverse is its inverse. So when we compose this bijection with its inverse, it was defined mapping set X into set X. It's a bijection. We'll get the identity on set X. So we get 1 sub X down here. Now we have this diagram that commutes. Okay, here comes the equivalence argument. Remember, phi and psi were uniquely determined. The freeness gave us the unique determination of these. We're trying to establish that we've got a mapping which gives us the identity. And we're about to show that this composition of functions, this composite function, equals the identity on F as follows. Okay, diagram over here on the right, we've got psi composed with phi, composed with I first, then psi and phi, maps X into F, by the way. That must equal I composed with the identity, identity first followed by the I, and that's the order we write them in. Of course, that's just the same as I, with the 1 sub X thing disappearing. We've got equality here. But also, we take upstairs, if we take this function to be the identity on F, and remember this function was uniquely determined by the freeness of F and F prime, we could take that to be 1 sub f, and we'd still have 1 sub f composed with I. We'd still have this followed by 1 sub f equals I, taking 1 sub f in place of the uppermost. You still get the equality, but this other information was to uniquely determine what mapping you have here, and the mapping you have here could well be the identity 1 sub f. Well, if it's unique and it could be 1 sub f, it must be 1 sub f because it's unique. That is, we must have the condition that psi composed with phi equals 1 sub f. And that's half of equivalence. Now all we need to do is show, reverse the orders. Show phi composed with psi equals 1 sub f prime. The mapping will be in the other direction. Similarly, we can show phi composed with psi equals 1 sub f prime. Actually, how you do it is interchange these two things. Put this one on the right and this one on the left, and then we'll have a mapping from f prime through f to f prime. And you'll get on top, you'll get the composition phi composed with psi. So these get interchanged, and it's the same argument. And you'll get then an identity on f prime, because you'll have a mapping then from f prime through f to f prime itself. Very similar, almost identical to what we just did, just doing some things in a different manipulation of the diagrams. And that's what equivalence is. Exactly these two little statements right here. There exist phi and psi, compose in one direction, get an identity, reverse that order, also get an identity on the appropriate objects. So there's the equivalence of free objects, provided they're free on sets of the same cardinality. So where we stand at this stage of the section, to summarize, we've seen that any two products or coproducts for a given family of objects are actually equivalent. And we just showed two objects that are free on the same set are equivalent. Actually, we showed something a little bit more general than that. We showed any two objects on sets of the same cardinality are equivalent. So of course, a set has the same cardinality as itself. So if we had both of these free on set X, we'd be good to go. We needed the bijection thing. So having maybe two sets of the same cardinality was useful in creating the diagrams. So let's introduce a final idea and prove a final result. It's a brief one. An object I in category C is called universal. I think that's probably a more common term than initial, though initial is more suggestive of what happens in the definition. So I is an object in category C if for each object C in category calligraphy C, there exists one and only one morphism mapping I to C, then that I is called universal. Initial makes sense because that means I can map I to anything else in that sense. I comes first. It's universal in the sense that I can map I to anything. So arguably, I guess both of those are reasonable, but we're mapping I to C. The I comes first. That's universal. Co-universal, of course, going to swap the orders on the mappings. An object T of C is co-universal or terminal if for each object C in category calligraphy C, there exists only one morphism mapping C to T. So T terminal, that makes sense. It's on the right-hand side in this little mapping notation stuff here. And that's a definition of co-universal. So only for universal, only one morphism coming out to any specific object. Co-universal, only one morphism coming in from any given object. All right. Yeah, of course, we just reversed an arrow between universal and co-universal. So I expect to be able to get some kind of dual statements with these things as well. If I can proves something for universal elements, then probably you can prove it for co-universal as well. All you do is reverse directions. And that's how the proof goes in Theorem 1710, which says, any two universal objects in a category are equivalent. Also says any two co-universal objects in a category are equivalent. So these are, I don't know, kind of special objects in the category. I'd be tempted to try to set up equivalence relations, but equivalent and equivalence are maybe subtly different. Sets have equivalence relations on them. Objects in a category have this equivalent thing on them, and it reminds me of some similar type behavior. But I probably shouldn't take that very far. Let's go through the proof of this. Let's show any two universal objects in a category are equivalent. Proof is quite brief. It's a single slide. Okay. Suppose I and J are both universal objects in category calligraphy C. Since I is universal and J is an object, any old object, then there's a unique morphism F that maps from I into object J. Now reverse the roles of I and J. Similarly, since J is universal and I is an object, then there's a unique morphism, call it G, mapping universal object J into object I. So if we take the composition, G composed with F, that maps I into itself. Compositions of morphisms is a morphism. That's in the definition of category. But 1 sub I maps I into I is also a morphism of C. Now we said I was universal. So there's only one morphism mapping I to I. I is universal. There's a unique morphism mapping I to I. This maps I to I, G composed with F. So does this 1 sub I type identity. So those must be equal by the uniqueness claim. Take that same argument, basically interchange the roles of I and J, and you'll get F composed with G equals the mapping, the morphism 1 sub J. Take this composition equals 1 sub I. This composition in the other order gives 1 sub J, and that's what equivalence is. Therefore, I and J are equivalent. You want to do co-universal, it's quite similar. Interchange the roles maybe of F and G, the mappings going in the other directions as needed for the co-universal idea. So universal objects in a category are equivalent. Co-universal objects in a category are equivalent. If we look again at the category of all groups, our claim is the trivial group is a universal group. That's going to mean the existence of unique morphisms. In the category of all groups, the morphisms were homomorphisms, by the way, as we saw in the previous example. Claim is trivial group, the group generated by the identity is the notation there, is universal because there's only one homomorphism mapping the identity into group G. You only got one element. Where are you going to map it to? Have to be mapped to the identity property of homomorphisms. So there's only one mapping, only one morphism in this category that maps this thing into any given group G. Also, the trivial group is co-universal. If I want to map group G to the identity, there's only one way to do it. You map all the elements of group G to the identity. And the fact that there's only one, we've reversed the order of the mapping here, tells you that that trivial group is also co-universal. So there's our run-in with category theory. Next section, 1.8, we'll look at products of groups, and we'll see this idea of product in a category pop up again. And the way we define a product of groups will give us an object in the category of all groups, it turns out. So that's the first place we'll use this, and then we'll use it sporadically throughout the rest of the group theory. So have a nice day. I'll see you in section 1.8 in the near future. Bye-bye.